Everything you see around you is made of matter. Your screen, the air you breathe, the ground beneath your feet. But according to the laws of physics, there should be something else out there. A perfect mirror image of matter called antimatter. This isn't just a theory. We've actually created it in labs, trapped it, and even moved it between buildings as if it were any other scientific sample. Yet, despite all our progress, a huge question remains. Why isn't the universe filled with both matter and antimatter? Why is everything we observe made of just one kind? That's the puzzle scientists at CERN have been trying to solve for years. And recently, they stumbled upon something unexpected once again. Researchers working with one of CERN's most advanced detectors observed strange behavior in antimatter, something that shouldn't be happening according to our current understanding. It's not just that antimatter is rare. It's that it doesn't behave the way we expect it to. The more we learn, the more it seems to slip through our fingers. So, what's really going on with antimatter at CERN? Why are experts more confused than ever, even after constructing billion-dollar machines to study it? And could these odd findings point toward new physics, something beyond what we thought we knew? The story begins at the dawn of the universe. Right after the Big Bang, equal amounts of matter and antimatter should have been created. That's what our best models tell us. For every proton, there should have been an antiproton. For every electron, a positron. And when these pairs meet, they annihilate each other, leaving behind pure energy. But look around. We're still here. The stars, planets, and galaxies are all made of regular matter. There's no sign of widespread antimatter. This imbalance is puzzling because it shouldn't exist. Yet, in the earliest moments after the Big Bang, something caused a tiny excess of matter to survive. That tiny surplus is everything we see in the cosmos today. We're talking about a difference of just one particle in a billion. The rest vanished in mutual destruction. The big question is, why did this happen? Physicists call this the baryon asymmetry problem. In simple terms, it asks where all the antimatter went and why matter came out on top. It remains one of the biggest unanswered questions in science. And it's not just a theoretical curiosity. If we could understand what caused that initial imbalance, we'd be closer to answering why anything exists at all. That's why CERN built machines like the Large Hadron Collider. It's not just about smashing particles. It's about hunting for the smallest differences between matter and antimatter. Because if we can catch antimatter behaving differently, even slightly, we might find the clue we've been searching for. And recently, they observed something unusual again. Let's talk about CP violation because that's where things get interesting. CP symmetry is the idea that if you take a particle, turn it into its antimatter version, and flip it as if looking in a mirror, the laws of physics should remain the same. That was the rule, but it turns out the rule isn't perfect. Decades ago, scientists detected small violations of this symmetry in certain particles. Even though the effect was tiny, it suggested that matter and antimatter aren't perfect opposites. But here's the catch. Those particles decay too quickly, and the violations aren't strong enough to explain the cosmic imbalance. We need something more significant, something that happens in baryons, the same family of particles that includes protons and neutrons, the building blocks of atoms. This year, it finally happened. CERN's LHCb experiment, which focuses on matter-antimatter differences, announced it had observed CP violation in a particle called the Lambda-B baryon. This is a heavy particle made of 3 quarks, similar to a proton but with a different quark composition. For the first time, physicists saw clear evidence that these baryons don't act the same as their antimatter twins. This is a big deal. The asymmetry they measured was small, around 2.5%, but in particle physics, that's enough to get attention. The statistical significance was over 5 sigma, meaning the odds of this being a random fluke are less than 1 in several million. In other words, it's real. Now, this doesn't mean the antimatter mystery is solved. Not yet, but it gives researchers a new direction. A new class of particles where matter and antimatter might not be identical. If these differences add up over time, they could explain why matter survived the early universe. It's one of those moments where a door doesn't swing wide open, but it cracks just enough to let new light in. And suddenly, the scientific community is paying close attention. Because if baryons like the Lambda-B behave differently from their antimatter counterparts, then maybe protons and antiprotons do too. Perhaps the fundamental stuff we're made of isn't as symmetrical as we believed. And that could be the key to understanding our universe. But that's only one piece of the puzzle. Because while the Large Hadron Collider studies high-energy collisions, something even stranger is happening in another part of CERN. Scientists are attempting the seemingly impossible. They're working on putting antimatter in a truck. It might sound like science fiction, but that's exactly what's happening. For the first time in history, researchers successfully transported a cloud of protons, which stand in for antiprotons, across the CERN campus using a specialized mobile trap. They built a high-tech container to safely hold these charged particles and drove it several kilometers, proving that one day, real antimatter could be moved the same way. Why is this such a big achievement? Because antimatter is incredibly difficult to handle. The instant it touches regular matter, both vanish in a burst of energy. You can't put it in a jar or a metal tank. It has to be suspended using magnetic fields inside a vacuum, inside a carefully designed trap. It's like trying to carry a drop of pure sunlight without getting burned. So why take the risk? The answer is precision. While CERN's antiproton decelerator is excellent for creating antimatter, the facility is surrounded by strong magnetic fields from other equipment. These fields can interfere with delicate measurements. So, scientists developed a method to move these particles to a quieter, more controlled lab environment, specifically to a facility in Germany with better shielding and less interference. The mobile trap kept a cloud of protons stable and isolated for over 12 hours during the trip. This success opens the door to new experiments that were once thought impossible. Soon, researchers will be able to test how antimatter behaves in different settings, not just at CERN but in labs across Europe and eventually around the world. This changes everything. It's no longer just about studying antimatter where it's produced. It's about preparing to use it, send it, and explore new frontiers. We've moved from creating antimatter in fixed detectors to proving we can transport it safely. That's a critical step toward making antimatter portable. It might sound like a small advance, but in experimental physics, it's huge. It means new collaboration, advanced technologies, and much more accurate tests of one of the universe's most mysterious substances. And while this is happening, another team is asking an even more unusual question. What if antimatter doesn't fall the same way regular matter does? What if gravity affects antimatter differently? It might sound like a silly idea. If antimatter is the opposite of matter, does it fall upward? At CERN, that's not a joke. It's a real experiment. This is one of the most overlooked problems in physics. How does antimatter respond to gravity? If you drop an antimatter ball, does it fall to the ground like a normal one, Or does it do something else? Does it fall slower, faster, or maybe in the opposite direction? The last possibility is unlikely, but until recently, no one could say for sure. In 2023, two major experiments at CERN conducted detailed tests to find out. One was called AlphaG, an extension of earlier experiments. The other was G-bar, short for gravitational behavior of antihydrogen at rest. These names sound technical, but their goal was simple. Create a small cloud of antihydrogen atoms, release them, and observe what happens. To do this, the atoms had to be neutral, with no electric charge, because any charge would distort the results. The challenge was to isolate pure antihydrogen and keep it perfectly still inside a vacuum chamber using magnets. Then let it go and watch how gravity acts on it. It sounds straightforward, but it's incredibly difficult. These atoms are extremely fragile. Conditions must be perfect. The fall distance was just a few centimeters. You're basically trying to detect the gravitational behavior of a ghost, but they managed to do it. And here's what they found. Antihydrogen falls downward, just like regular hydrogen. According to the AlphaG results from 2023, it accelerates under Earth's gravity in the same direction and at a rate consistent with matter, within the limits of experimental precision. G-bar is still working on similar measurements, aiming to confirm these findings with even greater accuracy. But the data also hinted at something odd, just a suggestion that the acceleration might be slightly different. Not enough to rewrite the laws of physics, but enough to make researchers look twice. Some results from G-bar were also slightly off, though still within the margin of error. Nothing conclusive, nothing earth-shattering, but not perfectly ordinary either. If antimatter behaves even a little differently under gravity, it could challenge everything from quantum field theory to general relativity. Einstein's equivalence principle, which states that gravity affects everything the same way regardless of composition, has never been thoroughly tested with antimatter until now. While early results suggest antimatter follows the same rules, physicists aren't done testing. Even a deviation of just 0.1% would be enough to shake the foundations of physics. So they're running more tests, refining measurements, and increasing sensitivity. Because in this kind of science, it's the tiny discrepancies that often reveal where our understanding is flawed. And when something breaks in physics, that's when things get exciting. But while all this is going on, the colliders, gravity tests, and transport experiments, another antimatter project is preparing to do something even bolder. They're not just dropping antimatter anymore. They're planning to fire it at unstable atoms on purpose. So, where does antimatter actually come from? You can't mine it, and you won't find it lying around. At CERN, antimatter is produced in one of the most advanced parts of the facility, a place most people have never heard of. It's called the antiproton decelerator, or AD for short, and it does exactly what the name suggests. It slows down particles that can't be touched. Here's how it works. First, high-energy protons are fired into a dense metal block. The collision produces a shower of exotic particles, including antiprotons. These are the antimatter versions of protons, and they're born moving incredibly fast, too fast to study. So the AD steps in to slow them down. We're talking about reducing their speed by a factor of 100,000 or more. You can't study antimatter when it's moving like a bullet. You need it calm, cold, and almost motionless. That's where ELENA comes in. ELENA is a smaller circular accelerator connected to the AD. But instead of speeding particles up, it slows them down even further. Think of it as a cooling ring for antimatter. ELENA can slow antiprotons to just a few millionths of the speed of light, gentle enough to trap them with magnetic fields. Once they're slow enough, scientists can capture them in highly specialized experiments. There's alpha, which traps antihydrogen and tests gravity. There's base, which compares the magnetic properties of protons and antiprotons with incredible precision. And there's asacusa, which studies the internal structure of antihydrogen using laser spectroscopy. Each of these experiments is searching for the tiniest differences between matter and antimatter. Differences that might explain why the universe looks the way it does. If they find something, even a small anomaly, it could change how we think about symmetry, time, or the Big Bang itself. What's impressive is the contrast. On one side, you have massive detectors where particles collide at nearly the speed of light. On the other, you have tiny chambers cooled to near absolute zero, designed to gently hold a few antimatter atoms as if they were made of glass. This is the antimatter factory. Not just one machine, but an entire ecosystem of experiments. Each has its own focus, its own questions, and its own piece of the puzzle. And now, this entire system is about to take on an even more ambitious task. They're planning to take that carefully stored antimatter and fire it at some of the strangest atoms in the universe, unstable radioactive nuclei. Because maybe the answers aren't in smashing matter and antimatter together. Maybe they're in how they interact. That's the goal of CERN's next major antimatter mission, called PUMA. You've heard of particle accelerators and antimatter traps. But now, scientists are planning something that sounds like science fiction. They're going to take 1 billion antiprotons and bring them face to face with unstable atoms, nuclei so rare and short-lived they don't exist naturally. It's called PUMA, which stands for Antiproton Unstable Matter Annihilation. This is one of the most ambitious antimatter experiments ever planned. Here's the idea. CERN has two main research areas. One is where the antiproton decelerator and ELENA are located, producing and slowing antimatter. The other is a facility called unsolved, where physicists study exotic atomic nuclei that decay in fractions of a second, created artificially from nuclear reactions. Normally, these two areas don't interact. Antimatter stays on one side, radioactive nuclei on the other. PUMA will change that. Researchers are building a mobile antimatter trap strong enough to hold over 1 billion antiprotons stable and isolated for hours. The trap will be moved from the antimatter lab to unsolved, where those antiprotons will be released in a controlled beam onto unstable atomic nuclei. Why? Because when an antiproton hits an atomic nucleus, it annihilates with a proton or neutron, and the debris from that collision provides incredibly precise information about the structure of the nucleus. In other words, antimatter becomes a kind of microscope, a tool for probing the inside of radioactive atoms that are normally impossible to measure. This hasn't been done before, not on this scale. The hope is that by studying how antiprotons interact with these exotic atoms, scientists can learn more about the forces inside atomic nuclei, especially in regions called neutron skins, where unstable atoms often have lopsided shapes. It could even hint at new nuclear physics, perhaps beyond what the standard model can currently explain. And the really remarkable part is that this experiment involves moving antimatter between buildings by truck. That alone is a scientific milestone. It's hard enough to keep antiprotons from touching anything in a static lab. Keeping them stable during transport, with temperature changes and mechanical vibrations, is a huge challenge. But if PUMA succeeds, it could transform antimatter research. Antimatter wouldn't be locked to a single lab anymore. It could travel to new experiments, new materials, and maybe even new countries. That opens the door to entirely new types of research that haven't even been imagined yet. But despite all this progress, CP violation in baryons, gravity experiments, precision spectroscopy, and now mobile antimatter, there's still a lingering problem. Nothing so far has fully explained the big mystery. Why is there more matter than antimatter in the universe? The data keeps improving, the tools keep evolving, but the answers still aren't clear. You'd think with everything happening at CERN, the discoveries in CP violation, the precision tests, the antimatter drops, the billion-dollar detectors, by now we should have found something major, something that clearly shows where the standard model breaks down, something that finally answers the antimatter question. But that's the frustrating part. After all this work, the laws of physics still mostly hold. The experiments are impressive. The measurements are historic. But when you step back, they all point to the same uncomfortable truth. Nothing we've observed yet is enough to explain why the universe favors matter. That CP violation in baryons is real and exciting, but the numbers still don't add up. The asymmetry is too small to account for the vast imbalance in the early universe. The gravity tests with antihydrogen show that, so far, antimatter falls downward like regular matter. No dramatic surprises, no strange repulsion, at least not yet. The BASE and Asymmetry experiments are checking for the tiniest possible violations of CPT symmetry. The idea that flipping charge, parity, and time together should make no difference. But those tests have been so precise that any deviation would have made headlines. And it hasn't. It's like chasing a ghost. We know it's there. Something must have tipped the universe toward matter. But every time we think we're getting closer, the data says not quite. To be clear, this doesn't mean the experiments have failed. Far from it. Every result, even a negative one, sharpens our understanding. It rules out wrong paths. It tells theorists where not to look. It closes doors so we can focus on the ones that are still open. But scientists are stumped, and they're not hiding that. In some ways, this honesty is what makes the pursuit so compelling. CERN isn't pretending to have all the answers. They're admitting that the universe is still hiding something deep and subtle. Maybe it's a new particle we haven't detected yet. Maybe it's a force we don't understand. Or maybe it's a breakdown of symmetry so small it's like trying to hear a whisper in a thunderstorm. That's the reality of modern physics. You can build the most powerful machines, run the cleanest experiments, trap the rarest particles, and still end up with more questions than answers. It's not a failure, it's a clue. Because when the rules stop working at the edges, that's where discovery truly begins. For now, the antimatter mystery remains just that, a mystery. We've ruled out many wrong answers. We've narrowed the possibilities. But the final piece of the puzzle is still missing. And yet, it's that very uncertainty that keeps scientists going. Because in physics, confusion isn't the end of the story. It's where things start to get interesting. The deeper we explore antimatter, the more questions arise. We've moved beyond theory. We've isolated antiprotons, trapped antihydrogen, watched it fall, and even packed protons into a high-tech trap and drove it down the road. Yet the core question remains. Why is the universe full of matter and not antimatter? It's not for lack of effort. CERN has built some of the most advanced tools humanity has ever made, all to get closer to that answer. And they're not done. The LHCb experiment is still running. The antiproton decelerator and ELENA are still feeding experiments. New missions like PUMA are just getting started. But this isn't about proving a theory anymore. It's about listening closely to what the universe is quietly trying to tell us. Because somewhere, hidden in all these results, is a hint of something bigger, something we've overlooked. Right now, scientists aren't claiming victory. They're doing something harder. They're admitting the mystery isn't solved. And in a field built on answers, that kind of honesty means one thing: they're getting close. Because every time a result comes back almost but not quite, it pushes us a little further beyond what we thought we knew. And that's where real discovery begins. So if antimatter keeps breaking the rules, that's a good thing. It means the rules are ready to change. If you enjoyed this journey into the strange world of antimatter, don't forget to subscribe, like, and share this video with others who love exploring the mysteries of the cosmos.